Alright, so today we're looking at predicting redox reactions. If you were in Mr. Shelley's class, you've already kind of taken a look at this. But we'll go through some stuff, and it'll be a bit of a review here before we figure out what's going to react with what. Okay, so predicting redox reactions. So redox reactions, we have a transfer of valence electrons from one substance to another. And we're transferring from what to what? Does anybody remember? From Ra to OA, right? We have a transfer of electrons from Ra to OA. And if I take a whole bunch of stuff and I throw it in solution, or if you have a few different things reacting in solution, knowing what is the strongest OA, what is the strongest Ra can help us figure out exactly where, what's going to react and where the electrons are going to transfer. Alright, so the number of electrons gained by one entity should equal the number of electrons lost. We've seen that when we were doing the half reactions, right? If your lead gained 2 electrons, that's not a very good example. That worked. If your lead ion gained 2 electrons and something else lost, right, they'd be gaining and losing the same amount of electrons. They should always be equal. And so they're constantly kind of in this tug of war for electrons. Again, just to reiterate, if you are being reduced, you are gaining electrons. So remember, we have that Leo says Ger. So lose electrons is oxidation, gain electrons is reduction. From that, though, we also figured out if you are losing electrons and you are being oxidized, so you've lost electrons, you threw your electrons away, that means you're causing another substance to be reduced. That means that's causing another substance to gain electrons. So we call that the Ra. And Ger, so if you're gaining electrons, you're causing the loss of somebody else, so you are the oxidizing agent. So the reducing agent is oxidized and the oxidizing agent is reduced. And we did that the first few units over and over and over again, because they're gonna ask you, like, which one lost electrons, which one gained electrons, what's the OA? What's the Ra? And you have to be able to identify those. And so just again, talking about the electrons. Okay, so today we're going to take a look at our data booklets. And so we did a whole bunch of making half reactions. A lot of the half reactions that we made are already in the data booklet. But you have to know how to make them, especially the acidic and basic half reactions, because they are not given in there. So it's just kind of a progression. Okay. We already can kind of look at that. Yes, thank you. Okay, so we're going through, we're going to predict redox reactions. And so your data booklet on page 7, that's where I'm looking at. Hopefully you turn to there. So we're looking at the data booklet on page 7. And so page 7 lists a whole bunch of reduction half reactions. So going in this direction is the reduction half reactions. How can you tell that those are reduction half reactions other than the fact that it tells you at the top of that table? The electrons are all over here, right? That's telling us the electrons are here, right? They're all gaining electrons. They all have electrons as part of the products. So they needed to gain that in order for the reaction to progress from the left to the right. That means that if these are all the reduction half reactions, if I come back this way, then what type of reaction would that be? That would be my oxidation half reaction. And so, you can see the little arrows here are saying that this reaction can go both ways. Just depends on what entities are present, if it's going to go and be a reduction reaction, or if it's going to go and be a oxidation half reaction. You see these electrical potentials here. You don't need to worry too much about those for now, but we will eventually get to them. Okay, so if this is my, and I just kind of zoomed in here, if this is my reduction half reaction, up here, and so you can see the voltage here kind of indicates which is the strongest, which is the weakest. So if these are all reduction half reactions, would these guys be RAs or OAs? RAs or OAs? OAs. So at the top of my table in my data booklet, I'm going to put that this is a SOA up at the top. That means that is that's where all the strong oxidizing agents hang out. The strongest oxidizing agent then, according to my table, is what? That's top left. Right, because the reduction after reaction is going from left to right. And so, what is the strongest oxidizing agent on this table? Pardon me? Fe, right? And if you remember, fluorine is the most reactive non-metal anyway, so kind of makes sense. Pardon me? What did I say? Sorry, yes, sorry, fluorine. I said fluorine, but then I said Fe. Sorry. Yeah, fluoride. So strongest, so this is my SOA. And then down here then, if I'm looking at the reactions progressing in this way, so those are the oxidation reactions. So down here, if these are all really strong oxidation reactions, we would call those guys what? The SRA. So this down here then is the SRA. So the strongest oxidizing agents are at the top left. The strongest reducing agents are on the bottom right. If you wanted to go further, you could say to yourself, okay, so this is the SOA. That means these guys are all being reduced when I'm going this way. And we'll add some more stuff there once we further in the electrochemistry unit, but we'll just say SOA is reduced. The SRA is then oxidized, and that's going to be when I'm progressing that reaction to the left. Alright, so everybody's got that written in their data booklets? Alright. And so I just kind of was saying there that as we move up the table, the strongest oxidizing agents are at the left. As I move down the table, the strongest reducing agents are on the right. So in the data booklet, we have a flow of electrons from the bottom right to the top left, which makes sense because my electrons are going to transfer from RA electrons to my OA. Ooh, that's hot. Yeah. Tastes like paper. It's like the 17th time today I nuked or two. I just need one. It just takes me all day to drink it. Alright, okay. And we should already know this, but electrons will flow spontaneously from the strongest reducing agent to the strongest oxidizing agent. That means that we don't have to put in any additional energy. I don't have to stir it. I don't have to add electricity. I don't have to add a catalyst. I don't have to add heat for these reactions to occur. If you have a strong OA and a strong RA, and they're both in the same solution or both in the presence of each other, they will automatically react. And so knowing these things is important, like especially like in the back in the chemistry room, there's certain substances I can't have next to each other because they're going to just want to react. They're going to naturally have that flow of electrons from one compound to the next. So in the back, right, my oxidizing agents are far apart from my strong reducing agents. Okay, so spontaneously, no electrons. Well, I'm not sure in the first part, but once we like kind of have the concepts for redox and we add those to like electrochemical cells, we'll do reactions there. All right, and so that takes us to the spontaneity rule for all reactions. Did I get you guys to write this down? Yeah. So a spontaneous redox reaction will occur if the oxidizing agent is above the reducing agent on the table. So a spontaneous reaction occurs if the OA is above the RA on your table. So your OA has to be above your RA in order for a reaction to occur. So what this means is I'm going to use my table. I would go find my oxidizing agent. if the oxidizing agent is on the left, is above the reducing agent on the right, right? If it's on the left, is above, then I will have a spontaneous reaction. If the OA is below the RA, I will have a non-spontaneous reaction. And in order for that to happen, I would have to add electricity or heat or something in order for that reaction to progress. So if the OA is above the RA, it's going to be spontaneous. Did everybody fill in those little bubbles there? Everybody make sure you fill in those little rectangles. All good? Everybody, these rectangles are on your, what do you call it? Note package. You bruise your apple. Ugh, the worst. As well as not even eat it. Okay, make sure you fill these out. It's good to have. Alright, so let's just go take a look at some examples here. We'll grab our data table, and look at this. So, I'm gonna write these, how am I gonna do this? I'm recording for Amy and them, but we'll figure this out. Alright, so zinc metal is mixed with a silver nitrate. So, zinc metal is gonna be in what state? Solid. Does it have a charge? No. Alright, is mixed with silver nitrate. We have figured out that nitrate, is that ever reacting? Hasn't reacted, right? We haven't seen any reaction with nitrate. So we're going to assume that it is going to be a spectator ion. And so silver is going to be just a solid or is it an ion? Ion, right? Because it was part of this compound and we're going to assume that it's in water. So it's Ag plus aqueous. And so I'm going to go to my table and look for zinc solid, and Ag plus aqueous. So I'll head to my table. I'm just going to bring this one up. So, erase all my ink here. So I need to go find zinc solid. Now, if I'm looking for a metal, is it going to be on the left or is it going to be on the right? Well, I can't technically, but it's probably going to be, so zinc is right here, zinc solid. And I'm looking for silver, Ag plus, and it's going to take a while for you to kind of get used to navigating through this chart. Ag plus, and it takes me a while to even remember, Ag, there you are, right there, right? And so, that means that Ag plus is what? The silver ions are what? My OA, and because it's to the left, and zinc is my Ra. And so my OA is above my RA, and therefore that reaction would be what? Spontaneous, right? Okay, I'm going to do one more, and then I'll let you do the rest of them. So lead metal, PV solid, excuse me, is mixed with cobalt nitrate. So cobalt, I just need to go look at my ion charge. Cobalt most common is going to be a 2+ aqueous. So I will go now look for those on my table. So PB solid and CO2+. So if I go back to this table here, I'm just going to change colors. Let's go red. So I'm looking for lead solid, should be on the left. So lead solid, that would be my Ra if it's on the right. And cobalt as a 2+. Cobalt 2+ is right here. It's a OA. So would that be spontaneous or non-spontaneous? Non-spontaneous, right? How do I know what side it's going to be on? So most of the time, if it's just a solid metal, it's going to be over here. If it's an ion, it's probably over here. Now, there's exceptions, like especially when you're talking about polyatomic ions, like, tin can be in multiple places. Like the tin 2 ion is here. The tin 2 ion is also here. It acts as both an OA and an RA, but we'll talk about that later. But generally, as a rule of thumb for what we're dealing with, metals are going to be on the right and ions are going to be on the left. It might not always follow that, but that's the quickest way to look for it. Okay, so we just said this here was a non-spontaneous reaction. So I want you to take a few minutes here and figure out, is C, D, E spontaneous or non-spontaneous? Okay, so nickel metal in a solution of silver ion. So you guys went to the, consulted your charts. What do you figure? Spontaneous or non-spontaneous? Spontaneous. Yep. Zinc metal and aluminum ions. Non. And copper 2 and iodine. Perfect. Everybody got the same thing? Again, it takes a while to learn to navigate through that, but what time is it? Okay, we're going to keep going for a little bit. Alright, so here we go. Old diploma question. See if you can answer it. Which of the following equations represents a spontaneous redox reaction? Take a second, see if you can figure it out. If you're answering the question, you should consult the chart. Check where zinc positive is and lead positive. If the OA is above the RA, that's spontaneous. So that would be non-spontaneous. You would check where tin 4 ions and iron is. That ends up being spontaneous. I think I have one more, so. Good one. Alright, so the reducing agent, they're throwing in concentrations here just to mess with your head. So the reducing agent that can convert tin 4 ions, so we're going to have a half reaction that goes from this to this, but not tin to, but not this to this is what? See if you can figure out that question. So go look at where these half reactions are, and then go look at where all of these metals are in relation to these. You can see that we're taking this question very seriously. Okay, so the question is asking you which of these 4 metals will convert or will react with tin 4 ions to produce this. So obviously you have to have 2 electrons in here. But it would not react with this. So I'm looking for some RA that's in between these 2 reactions. So if I go find these 2 reactions on here, here's my first reaction, tin 4 plus. I don't need it. And the second reaction is this. So which of them, so this is the OA, which of them is in between here? Lead. Everything else would be down here and would still be an RA and react with both of these, not just one of them. Does that kind of make sense for anybody who's listening? It has to be between them not to react, because we only want it to react with the tin 4. We don't want it to react with the tin 2. So it has to be between them. Not something down here is going to react with both. Yes, exactly. Something above wouldn't react with anything. Did I do that? Yes, I know. Where am I going to end? Okay. I'm just going to talk about building redox tables. Today I'm going to get you just to, once I'm done briefly looking at this, to just deal with spontaneity, and then we're going to build some redox tables tomorrow. If you were with Mr. Shelley, did you guys build redox tables? What did you do? Okay. How long did you spend on this? What's the whole time? The whole one class? Like. No. Okay. Okay, let's continue. So, building a redox table. So, we can build redox tables to figure out spontaneity. And so, a positive sign obviously means that a reaction is going to occur. We have to, first of all, know how to analyze these tables before I can move on. So, generate a redox table given the following data. So, using your table, what I want you to do is go fill this out. So if you have, if copper 2 plus reacts with copper solid, are you going to have a reaction? Okay, well, all of these can't react with each other. But, so what you're going to do is go see, would zinc 2 plus ions react with copper? Would it react with lead? Would it react with silver. If they do, give me a check mark. If it doesn't, just give me an X. And so I want you to go fill out that redox table. It's essentially just writing down spontaneous, non-spontaneous in the form of a table. So take a few seconds here and fill that out. Okay, so there's the table. Okay, hopefully your table is right. So then for part B here, oxidizing agents from strongest to weakest, whichever has the most check marks is the strongest. So Ag positive, Pb 2+, is that right? Oh, sorry, Cu 2+. Wrong way. Zinc, copper. Sorry. So Ag, then copper, then lead, then zinc. Okay, lead, and then zinc. If I go back, and so the reducing agents from the strongest to the weakest, what's the strongest reducing agent?
It's the top. First one, but opposite.
Right, so zinc, lead, copper, and silver. And so what you should notice is whatever happened here is the opposite for your oxidizing agents. Everybody got that? Okay. The last thing we can do, and the last thing that we're gonna have to start doing here, is taking all of these. Once I figured out which is the strongest oxidizing agent and the weakest, I can then make my own table of half reactions. And so to make my own table of half reactions, we said Ag is the solid, so I would say Ag positive plus how many electrons? 1 electron would produce Ag solid. So I'm going to essentially be creating my own reduction half reaction table for this question. So I would do silver, and then I would do copper 2+, produce plus 2 electrons, produces copper solid. I would do the same thing for lead. Lead solid, and the same thing for zinc, 2+, 2 electrons, right? And so, based off of that table, and it's very important to know how to do that table, because right now, everything that we're talking about is in your data booklet. They're going to give you reactions that aren't on here, and then you have to create your own table, and then create another half reaction table. And so you could put those in order to figure out which is the SOA, which is the SRA. Okay, so there's you try if you want to try that. But so for today, I'm gonna leave that here. We're gonna look at generating your own redox tables tomorrow from random information that they give you, not stuff that's in your data booklet. So for today, we're gonna say it's homework 3. It's only a few questions in there. Homework 3, numbers 1 to 3. Okay, homework 3, numbers 1 to 3.